Right now, the farthest human-made object ever built is drifting through space at over 60,000 kilometers per hour. Voyager 1 has been flying for nearly 50 years. It has crossed the edge of the solar wind, punched through the boundary where our sun's breath fades to nothing, and entered interstellar space. It is roughly 170 astronomical units from home, and it has not even begun to reach the Oort Cloud. The inner edge of that invisible shell sits more than 2,000 astronomical units away. The outer edge may stretch past 100,000. If Voyager 1 were a car pulling out of your driveway, it has not yet reached the end of your street, and the Oort Cloud is on another continent. If you enjoy journeys that stretch the mind past anything comfortable, do me a small favour and hit that like button, and if you have not already, subscribe so you do not miss what comes next. Now, get yourself comfortable. Let's begin. Open any astronomy textbook. Find the diagram of the solar system. There it is. A clean illustration with 8 planets arranged in concentric orbits around a yellow star. Mercury closest, then Venus, Earth, Mars, a stippled band for the asteroid belt, Jupiter, Saturn, Uranus, Neptune. Maybe Pluto appears as a small dot at the far edge, with a dashed orbit and a footnote explaining its reclassification. The whole arrangement fits neatly on a single page. The labels are tidy. The distances look manageable. You can trace the entire solar system with your fingertip in about 2 seconds. That diagram is wrong. Not slightly off, not rounded for convenience. It is wrong by a factor so extreme that calling it an oversimplification does not come close. If you corrected that image to true scale, the 8 planets would collapse into a space so small you could not print it. The entire zone from Mercury out to Neptune, every world you have ever been taught about, every rocky surface, every gas giant, every ring system, every moon, occupies less than 0.1% of the Sun's actual gravitational territory. Everything beyond that thin planetary ribbon belongs to a solar system you were never shown. A solar system that is darker, emptier, and so vast that the familiar planetary neighbourhood shrinks to a pinprick at the centre of something almost incomprehensibly large. Start with what we know for certain. Neptune orbits the Sun at an average distance of about 30 astronomical units. 1 astronomical unit is the distance from Earth to the Sun, roughly 93 million miles, or about 150 million kilometres. Neptune sits 30 times farther from the Sun than Earth does. That distance is impressive by everyday standards. Light from the Sun takes about 4 hours to reach Neptune. A spacecraft travelling at Voyager speeds would need over 12 years just to arrive. For most of human history, Neptune marked the outermost boundary of the known solar system, and that seemed like enough. When astronomers discovered Neptune in 1846, they believed they had found the frontier. The discovery itself was a triumph of mathematics. Scientists noticed that Uranus was not behaving as predicted. Its orbit wobbled in ways that suggested something massive was pulling on it from farther out. 2 mathematicians, working independently, calculated where that unseen body should be. When observers pointed their telescopes at the predicted position, Neptune appeared within a degree of where the math said it would be. It was one of the great victories of gravitational theory. The solar system had a new outermost planet, discovered not by luck but by the logical consequence of Newton's laws. For over a century afterward, the map expanded only slightly. Pluto was discovered in 1930, adding a small, frozen body orbiting at roughly 40 astronomical units on a tilted, eccentric path. But Pluto never quite fit the pattern. Its orbit was inclined more than 17 degrees to the plane of the other planets. It crossed Neptune's orbit during part of its long year. It was smaller than Earth's moon. For decades, nobody seriously questioned its status as the 9th planet. Pluto sat at the edge of the map, and the solar system ended there. Except it did not. The first cracks in this assumption appeared decades before anyone found proof. In the 1950s, the Dutch-American astronomer Gerard Kuiper speculated that a belt of frozen debris might orbit beyond Neptune, a leftover population from the disk of gas and dust that had originally formed the planets. The idea made physical sense. Planet formation is messy. Jupiter, Saturn, Uranus, and Neptune swept up most of the material in their neighbourhoods, but the space beyond Neptune was too sparse and too cold for another large planet to coalesce. Whatever debris existed out there should still be drifting, frozen and invisible, in a broad belt beyond the last giant. For 40 years, the idea remained theoretical. Nobody could find the objects. They were too small, too faint, and too distant for the telescopes of the era. The problem was not just distance, it was brightness. Sunlight at 40 astronomical units is roughly 1,600 times dimmer than at Earth's distance. A rock the size of a small city out there would reflect so little light that it would be fainter than a candle flame viewed from thousands of kilometers away. Telescopes of the mid-20th century simply could not detect something that faint moving that slowly against the background stars. Then, in 1992, astronomers David Jewitt and Jane Liu discovered a dim object beyond Neptune's orbit. It was designated 1992 QB1, and it was nothing dramatic to look at. A faint smudge in a long-exposure photograph, sitting at roughly 44 astronomical units from the Sun, but it confirmed something transformative. There was a population out there, not one lonely ice ball, a whole belt. What followed was an avalanche. Hundreds of small icy bodies turned up in survey after survey, occupying a broad zone, stretching from about 30 to 50 astronomical units. This region became formally known as the Kuiper Belt. It is real, directly observed, and now contains thousands of catalogued objects. Some are small, just a few tens of kilometers across. Others are substantial worlds in their own right. The discovery of the Kuiper Belt did not just add a few objects to the solar system roster, it fundamentally rewrote the outer boundary of the planetary map. Pluto was not a lonely misfit at the edge of civilization. It was the largest known member of an entire population that nobody had been looking for. The Kuiper Belt contains an estimated hundreds of thousands of objects larger than 100 kilometers across, and potentially trillions of smaller fragments. Several of these objects are large enough to earn the classification of dwarf planet. Eris, discovered in 2005, is nearly the same diameter as Pluto and slightly more massive. Marquet and Haumea orbit within the same general region. These are not pebbles. They are worlds with surfaces, compositions, and in some cases thin atmospheres and moons. Eris has a moon called Dysnomia. Haumea has 2. Pluto itself has 5 known moons, the largest of which, Chiron, is so big relative to Pluto that the two orbit a shared centre of gravity that lies in the space between them. They do not orbit each other the way the moon orbits Earth. They waltz around a point in empty space, a true binary system at the edge of the known solar system. The discovery of Eris in 2005 directly triggered one of the most controversial decisions in modern astronomy. If Eris was the same size as Pluto and even heavier, then either Eris was a 10th planet or Pluto was not really a planet at all. In 2006, the International Astronomical Union voted to reclassify Pluto as a dwarf planet, a decision that provoked public outrage but reflected a deeper scientific truth. Pluto was never a planet in the way Mercury or Jupiter is a planet. It was the brightest and most famous resident of a vast icy belt that everyone had been ignoring. NASA's New Horizons spacecraft brought this distant belt to life. Launched in 2006 and arriving at Pluto in 2015, it returned the first detailed images of Pluto's surface. The pictures silenced anyone who thought the outer solar system was boring. Nitrogen glaciers flowed across vast plains. Towering mountains of water ice jutted above the surface, some rising 3,000 meters high, comparable to the Rocky Mountains on Earth. A heart-shaped region of frozen nitrogen gas stretched more than 1,000 kilometers across, its surface so young and smooth that it must be constantly renewed by some internal geological process. Pluto had a thin atmosphere of nitrogen, methane, and carbon monoxide, hazing blue against the blackness of space in backlit photographs taken as New Horizons looked back after its flyby. There were signs of possible cryovolcanism, where instead of molten rock, slushy mixtures of water ice and ammonia may have erupted onto the surface. Pluto was not a dead grey rock. It was an active, complex world with geology that nobody had predicted, sitting in a part of space that had been drawn as blank emptiness on every map for a century. In 2019, New Horizons flew past a Kuiper Belt object called Arakoth, a small, reddish, two-lobed body, shaped like a flattened snowman. At more than 43 astronomical units from the Sun, Arakoth became the most distant object ever visited by a spacecraft. Its surface was remarkably smooth and uniform, coated in organic compounds that gave it a dark reddish hue. Scientists determined that Arrokoth had formed gently, through the slow coming together of two smaller bodies rather than a violent collision. Its pristine surface offered a glimpse of conditions in the earliest solar system, material that had been sitting in deep freeze for 4.5 billion years without significant alteration. Touching Arrokoth with instruments was like opening a time capsule sealed before the Earth had finished forming. And even Arrokoth is close. Staggeringly, laughably close compared to what lies beyond. The Kuiper Belt does not end in a clean line. It frays outward. Beyond the densest part of the belt, at roughly 50 astronomical units, there is a more scattered population of objects whose orbits are wilder, more elongated, more inclined. These bodies were not gently placed into circular paths. They were hurled outward by gravitational encounters with Neptune during the chaotic early history of the solar system. But to understand how they got there, you have to understand what the solar system looked like before it settled into its current shape, because the planets did not always orbit where they orbit now. The solar system we see today is the aftermath of a catastrophe. Within the first few 100 million years of the solar system's life, the giant planets underwent a dramatic reorganization that fundamentally reshaped everything beyond the asteroid belt. The best current models, building on a framework first proposed by researchers at the observatory in Nice, France, and refined many times since, describe a period of gravitational instability so violent that it scattered icy debris across distances of tens of thousands of astronomical units, and may have triggered a devastating bombardment of the inner planets. In the original configuration, the four giant planets orbited much closer together than they do today, packed into a tighter arrangement with a dense disk of icy planetesimals extending beyond Neptune's initial orbit. For millions of years, this configuration was stable. The planets orbited predictably. The debris disk sat undisturbed. Nothing hinted at the chaos to come. Then Jupiter and Saturn crossed a critical orbital resonance. Their orbital periods aligned in a ratio where Jupiter completed exactly 2 orbits for every one of Saturn's. This resonance amplified gravitational interactions between the two giants, pumping energy into Saturn's orbit and destabilizing the entire outer solar system. Saturn was pushed outward. Its new trajectory perturbed Uranus and Neptune. Within a geologically brief window, perhaps just a few million years, the outer planets scattered off each other like balls on a gravitational pinball machine. Uranus and Neptune may have swapped orbital positions entirely. Neptune was flung outward by several astronomical units, ploughing through the dense disk of icy debris that had been sitting quietly beyond its original orbit. The effect on the debris disk was devastating. Neptune swept through this belt of trillions of icy planetesimals like a wrecking ball through a warehouse. Its gravity flung objects in every direction. Some were hurled inward, where they crossed the orbits of the other giant planets. Jupiter, the most massive, ejected many of these inward scattered bodies from the solar system entirely, sending them on hyperbolic trajectories into interstellar space. Others were scattered by Saturn, Uranus, or Neptune itself onto wildly elongated orbits that stretched to thousands or tens of thousands of astronomical units before looping back. These barely bound survivors, carrying the energetic signature of their violent scattering, became the raw material of both the scattered disk and, eventually, the Oort Cloud. The inner solar system did not escape unscathed. Some of the inward scattered debris crossed the orbits of Mars, Earth, Venus, and Mercury. There is strong evidence that this period of planetary reorganization triggered a spike in cratering rates across the inner solar system, roughly 4 billion years ago, an event known as the Late Heavy Bombardment. The Moon's battered surface preserves the record. Many of the largest impact basins on the Moon, Mercury, and Mars date to approximately this era. If the bombardment hypothesis is correct, then the same event that built the Oort Cloud also scarred the surfaces of the terrestrial planets. The violence that created the solar system's most distant structure left its fingerprints on the worlds closest to the Sun. The survivors of this era became the scattered disk. They are not relics of calm formation. They are the wreckage of a planetary rearrangement that reshaped the entire outer solar system. Their eccentric, tilted orbits carry the permanent imprint of the gravitational chaos that launched them. The innermost part of the scattered disk overlaps with the outer Kuiper Belt, making the boundary between the two populations blurry. Astronomers debate exactly where one ends and the other begins, because the definitions are based on orbital characteristics rather than physical boundaries. But the outermost reaches of the scattered disk stretch far beyond anything the Kuiper Belt contains, extending into the enormous gap between the known populations and whatever lies farther out. Some scattered disk objects have aphelia, the farthest points of their orbits, at several hundred astronomical units. A few push past 1,000, and then there are the strangest objects of all. A small number of bodies have been found with orbits that are detached from Neptune's influence entirely. Their perihelia, the closest points of their orbits to the Sun, are so far from Neptune that the giant planet cannot be responsible for placing them where they are. These objects sit in a kind of orbital no man's land, too distant for the scattered disk, too close for the outer Oort Cloud, and unexplained by any interaction with known planets. They hint at something else entirely, something farther, something much larger, but that comes later. For now, the point is simpler and more jarring. The Kuiper Belt, the scattered disk, and all the dwarf planets in them represent only the first thin layer beyond the planetary solar system. They are the immediate suburbs, and even these suburbs stretch 30 to 50 times farther from the Sun than Earth does. The scattered disk pushes the frontier to hundreds of astronomical units. That alone would be enough to shatter the old textbook diagram. But the real shock is what comes after the suburbs end, because after the scattered disk, there is a gap, a vast, dark, apparently empty chasm between the last known populations and the beginning of the Oort Cloud. This gap stretches from roughly 1,000 astronomical units to perhaps 2,000 or more. No confirmed objects populate it. No telescope has surveyed it comprehensively. It is a desert between two oases, and it is enormous. Try to picture what this gap contains. Nothing that we know of. No icy bodies large enough to detect. No comets in stable orbits. No scattered debris returning from distant aphelia. Just space. Cold, empty, featureless space stretching outward for hundreds of billions of kilometers without a single landmark. The Sun is still visible from this region, still the brightest star in the sky, but it has already lost the appearance of a disk. It is a point of light, brilliant but small, offering no warmth and precious little illumination. An object drifting through this gap would be bathed in near total darkness, lit only by starlight and the faint cosmic microwave background, the residual glow of the Big Bang itself. This gap is not well understood. It may not be truly empty. Objects might exist within it that we simply cannot detect, bodies too small and too faint and too slow-moving to register in any current survey. The inner Oort Cloud may extend closer to the Sun than models predict, filling part of this gap with a sparse population of icy objects on stable but unobservable orbits. Or the gap may be real, a genuine depletion zone where the dynamics of planetary scattering and galactic tidal forces conspired to leave very little behind. Either way, it represents a frontier of ignorance. We know what lies on one side of it, the scattered disk and its detached outliers. We are confident about what lies on the other side, the inner Oort Cloud. But the space between remains one of the least characterized regions of the entire solar system. At Voyager speeds, crossing this gap alone would take centuries, and on the far side of that desert waits a structure so large it redefines everything we think we know about the solar system's size. Consider Voyager 1. Launched in 1977, it is the most distant human-made object in existence. It flew past Jupiter in 79, Saturn in 80, and then kept going, accelerating outward on a trajectory that would carry it beyond the planets entirely. As of 2026, Voyager 1 sits at approximately 170 astronomical units from the Sun. It is travelling at roughly 17 kilometers per second, about 61,000 kilometers per hour. Every single day, it puts another 1.5 million kilometers between itself and home. At this speed, Voyager 1 covers in 24 hours a distance greater than the diameter of Jupiter. It is moving fast by any standard that human experience can provide. The journey behind Voyager 1 is already extraordinary. It passed through the Jupiter system and discovered active volcanoes on the Moon, AEO, the first volcanic activity ever observed on another world. It flew through Saturn's ring system and photographed the intricate structure of thousands of individual ringlets. In 1990, at a distance of 40 astronomical units, Carl Sagan persuaded mission controllers to turn the camera around and take one final photograph of Earth. The result was the pale blue dot, an image in which our entire planet appeared as a fraction of a single pixel, suspended in a beam of scattered sunlight. Everything that had ever happened in human history, every war, every love, every birth and death and discovery, had occurred on that barely visible speck. Voyager 1 was only 40 astronomical units away when that picture was taken. It has since travelled more than 4 times farther, and Earth has long since vanished from any camera it could aim. In 2004, Voyager 1 crossed the termination shock at roughly 94 astronomical units, the boundary where the solar wind abruptly slows from supersonic to subsonic speed as it collides with the interstellar medium. The instruments registered a sudden change in the density and behavior of charged particles. The spacecraft had entered the heliosheath, a turbulent transitional zone where the sun's outward-flowing wind piles up against the pressure of interstellar gas. Voyager 2 crossed this same boundary in 2007 at 84 astronomical units, confirming that the termination shock is not a perfect sphere, but an asymmetric, shifting surface. Then came the heliopause. In 2012, Voyager 1 crossed this final boundary at approximately 122 astronomical units, passing beyond the reach of the solar wind entirely. The plasma environment changed dramatically. Solar particles vanished. Galactic cosmic rays surged. The magnetic field shifted orientation. Voyager 1 had entered interstellar space, the medium between stars. It was the first human-made object to do so. The announcement, when it came, was muted by the sheer strangeness of the data. Scientists spent over a year debating whether the crossing had actually occurred, because the transition was more gradual and more complex than models had predicted. Now, in 2026, Voyager 1 is approaching another milestone. By late this year, it will become the first human-made object to reach a distance of 1 light day from Earth. That is a landmark moment. Nearly 50 years of flight, and Voyager 1 will finally be far enough away that its radio signals take a full 24 hours to reach us at the speed of light. Its transmitter, powered by a decaying plutonium battery, sends signals at roughly 23 watts, the power of a refrigerator light bulb. Those signals, spreading outward across 170 astronomical units of space, arrive at Earth so faint that the receiving dishes of the Deep Space Network must strain to detect them. One by one, instruments aboard the spacecraft are being shut down to conserve power. The cameras went dark decades ago. The ultraviolet spectrometer was turned off. By the early 2030s, there will not be enough power to operate any instrument at all, and Voyager 1 will go silent forever. And it is nowhere close to the Oort Cloud. The inner edge of the Oort Cloud begins somewhere around 2,000 astronomical units from the Sun. Some estimates push it to 5,000. Voyager 1, at 170 astronomical units, has covered less than 9% of the distance to even the closest possible boundary of the cloud. At its current rate of about 3.5 astronomical units per year, Voyager 1 will not reach the inner edge for roughly 500 years. It will not exit the far side of the outer cloud for approximately 30,000 years. Think about what that means in human terms. 500 years just to arrive at the front gate. Voyager 1 was launched during the presidency of Jimmy Carter. 500 years before that, the year was 1526. The Protestant Reformation was barely underway. Magellan's crew had only just completed the first circumnavigation of the Earth. Most people believed the Sun orbited the Earth. No European had seen Australia. The entire span of modern science, every discovery from Copernicus to relativity to quantum mechanics to the detection of gravitational waves, fits within the time Voyager 1 still needs to reach the inner Oort Cloud. And arriving at the inner edge is just the beginning. The outer cloud stretches tens of thousands of astronomical units farther, 30,000 years. When Voyager 1 finally drifts past the last icy body in the outer Oort Cloud, more time will have passed since its launch than the entire span of recorded human history. Civilizations will have risen and fallen. Languages will have been born and gone extinct. The constellations in Earth's sky will have shifted into unrecognizable patterns, and Voyager 1 will still be coasting, silent and unpowered, Through a darkness it entered before the first Egyptian pyramid was built. The outer Oort Cloud may extend to 100,000 astronomical units from the Sun. That is roughly 1.5 light years. Alpha Centauri, the nearest star system to our own, sits about 4.25 light years away. The outer boundary of the Oort Cloud reaches a significant fraction of the way to the next star. The solar system is not a compact arrangement of planets huddled around a fire. It is a gravitational territory so enormous that its outermost possessions drift in a region closer to another star than to most of the planets they technically orbit. Now go back to that textbook diagram. Neptune at 30 astronomical units, the Oort Cloud at 100,000. If Neptune's orbit were drawn as a circle 1 centimetre across on your page, the outer Oort Cloud would be a circle more than 33 metres wide. It would not fit in your classroom. It would not fit in your school. You would need to draw it across a football field, and Neptune would be a dot the size of a grain of salt at the centre, and the 8 planets would be invisible, compressed into a space smaller than the period at the end of this sentence. The planetary solar system is not the solar system. It is the bright lobby of an unimaginably vast building, and almost nobody ever talks about the rest of the structure. Beyond the lobby, beyond the Kuiper Belt, beyond the scattered disk, beyond Voyager 1's lonely signal fading in the dark, there is a region of space so large and so cold and so empty that the Sun itself becomes just another star in the sky, and somewhere out in that region, stretching in every direction, trillions of frozen relics from the solar system's birth orbit in silence, too faint to see, too distant to visit, too numerous to count. They have been there for 4.5 billion years. Occasionally, something disturbs one of them. A gravitational nudge from a passing star, a slow torque from the galaxy itself, and that frozen body begins to fall, inward, slowly at first, then faster, drawn by a sun it can barely feel, on a journey that will take millions of years. If it survives the fall, if it crosses the scattered disk and the Kuiper Belt and the orbits of the giant planets, it will heat up. Its ices will sublimate, a tail will form, and for a few weeks a smear of ancient light will appear in Earth's sky, and someone will look up and call it a comet without ever knowing that it came from a place so far away that the Sun was just a dim star when the journey began. Those comets are the only direct evidence we have. They are postcards from a place we cannot visit, dropped on our doorstep by a gravity we can barely measure, carrying frozen chemistry older than the Earth itself. But the Kuiper Belt and the scattered disk are only the front porch. The real solar system, the terrifying one, begins where the light gives out and the evidence becomes invisible. No human telescope has ever directly imaged a confirmed Oort Cloud object sitting in the Oort Cloud. No spacecraft has visited one. No camera has photographed the cloud's structure from the outside. No survey has mapped its population. In every conventional sense, the Oort Cloud is invisible. Its objects are too small, too faint, too cold, and too impossibly far away to show up in even the most sensitive instruments ever built. At distances beginning around 2,000 astronomical units from the Sun, an icy body the size of a city reflects so little sunlight that it might as well not exist. By 50,000 astronomical units, the Sun is just another point of light in the sky, and anything orbiting out there is colder than the empty space between galaxies. And yet scientists are confident it is there. Not hopeful, not speculating. Confident in the way a detective is confident about a crime that nobody witnessed, because the evidence on the ground tells only one coherent story. The evidence arrives on its own, falling inward from the dark. Long-period comets are the Oort Cloud's confession. These are objects that take more than 200 years to orbit the Sun, and some take millions. Unlike short-period comets such as Halley, which return every 75 or 76 years on predictable paths linked to the Kuiper Belt, long-period comets appear without warning. They fall into the inner solar system on enormous looping orbits, blaze past the Sun trailing tails of sublimating ice and dust, and then swing back outward into the dark. Many of them are making their first known approach. They have never been this close to the Sun before, at least not within the span of recorded history, and some will never return. The comets themselves are small. A typical cometary nucleus is only a few kilometers across, a loose aggregate of ice, dust, and frozen gases held together by weak self-gravity. Some are as fragile as a snowbank. Others are denser, more consolidated, but still porous and structurally weak. When a comet approaches the Sun, heating begins at distances of a few astronomical units. Surface ices sublimate directly from solid to gas, bypassing the liquid phase in the vacuum of space. The escaping gas drags dust particles with it, forming a hazy envelope called a coma that can expand to tens of thousands of kilometers across. The solar wind and radiation pressure push this material outward, forming the familiar tail that can stretch millions of kilometers through space. The spectacle is dramatic, but the object producing it is tiny. The comet is a small, dark, crumbling body surrounded by an enormous cloud of its own debris. These visitors from the outer solar system were observed for thousands of years before anyone understood where they came from. Ancient civilizations regarded them as omens. Early astronomers tracked their paths across the sky and noted their irregular appearances. It was not until the 20th century that their true origin began to emerge. In 1950, the Dutch astronomer Jan Oort studied the orbits of these long-period visitors and noticed a pattern that no existing model of the solar system could explain. He built on earlier work by the Estonian astronomer Ernst Öpik, who in 1932 had proposed that a distant reservoir of cometary material might surround the Sun. Oort went further. He examined the orbital energies of 20 known long-period comets, tracing each trajectory backward to calculate where it had been before falling sunward. The process was painstaking. Each comet's orbit had to be corrected for the gravitational influence of the giant planets, which tug on comets as they pass through the inner solar system and alter their paths. Only after these corrections could the original, undisturbed orbit be reconstructed. 3 details stood out. First, the comets were not interstellar. Their orbits were bound to the Sun. They were not wanderers from another star system passing through. They belonged to our solar system, even though their paths carried them staggeringly far away. Second, the comets arrived from every direction. Short-period comets tend to orbit near the ecliptic, the flat plane where the planets travel. Long-period comets showed no such preference. They came from above, below, behind, ahead, at every possible angle. Whatever population they originated from was not a flat disk. It was spherical, surrounding the Sun in 3 dimensions like a shell. Third, when Oort calculated the farthest points of their orbits, the aphelia, they clustered, not at random distances, but near 50,000 astronomical units. Comet after comet reached its most distant point at roughly the same enormous distance from the Sun, suggesting a specific region of space where these objects spent most of their time. The clustering was not exact, but the pattern was unmistakable. This concentration of aphelia near a specific distance is now called the Oort spike, and it remains one of the strongest pieces of evidence for the cloud's existence. Something was out there, at tens of thousands of astronomical units, serving as a reservoir from which comets were occasionally dislodged and sent falling inward. The only structure that fit all 3 observations was a vast, roughly spherical cloud of icy bodies surrounding the entire solar system at extreme distance. Objects within this cloud orbit the Sun so slowly, taking millions of years per revolution, that they remain frozen and inert indefinitely. But once in a while, an external force shifts one of their orbits just enough. A gravitational nudge from a passing star, a slow tidal pull from the Milky Way itself. The nudge changes the object's path, lowering its closest approach to the Sun. It begins to fall. Over hundreds of thousands of years it spirals inward, gaining speed, until it crosses the orbits of the giant planets and enters the inner solar system. If it passes close enough to the Sun, its surface ices sublimate, gas and dust stream outward, and a tail forms. It becomes a comet, visible, temporary, a brief flare of evidence from an invisible source. Oort proposed this structure in 1950, and it now bears his name. The Oort Cloud is one of the largest inferred structures in astronomy, a region that may span from a few thousand to 100,000 astronomical units or more, containing perhaps 1 trillion icy bodies, and it was deduced entirely from the behavior of objects that left it. No one has ever seen the cloud itself. We see only the rain that falls from it. In the decades after Oort's proposal, astronomers refined the model. The cloud is no longer imagined as a single uniform shell. Instead, it is understood as 2 distinct regions, each with different characteristics. The outer Oort cloud is the classical structure Oort originally described. It begins at roughly 20,000 astronomical units and may extend to 100,000 or beyond. It is approximately spherical, consistent with the fact that long-period comets arrive from all directions. Its population is sparse. Estimates suggest roughly 1 trillion objects larger than 1 kilometer in diameter occupy this shell, with perhaps 1 billion larger than 20 kilometers. Despite these enormous numbers, the volume of the outer cloud is so vast that the density is almost non-existent. An object drifting through the outer Oort cloud could travel for years at interplanetary speeds without passing within millions of kilometers of another body. This is a structure defined by emptiness. A frozen museum with no visitors, where the exhibits are separated by distances that dwarf anything in the inner solar system. The inner Oort cloud, sometimes called the Hills cloud after the physicist Jack Hills, who proposed its existence in 1981, occupies the space between the outer cloud and the scattered disk. It extends inward from roughly 20,000 astronomical units to perhaps 2,000, forming a denser, more flattened structure compared to the spherical outer shell. The inner cloud is believed to contain significantly more mass than the outer cloud, possibly 2 to 5 times as much. Because it sits deeper within the Sun's gravitational well, its objects are more tightly bound and less easily disturbed by passing stars or galactic tides. This makes the inner cloud a reservoir that feeds the outer cloud over billions of years, replenishing the population that is slowly eroded by external forces. The relationship between the two regions is dynamic. The outer cloud loses objects constantly, to cometary infalls and to ejection into interstellar space. The inner cloud, more protected and more populous, gradually supplies replacements. Without this reservoir, the outer cloud might have been emptied long ago. In 2025, a team led by astronomer David Nasvorny at the Southwest Research Institute published a study that offered the first detailed look at the inner Oort cloud's possible shape. Using a NASA supercomputer, they simulated the formation and evolution of the cloud over the full history of the solar system. The simulation tracked how the giant planets scattered icy debris outward during the solar system's early chaos, and how passing stars and the Sun's birth cluster environment shaped those scattered objects over billions of years. Their results, posted to the preprint server and not yet peer-reviewed at the time of publication, were striking. The inner Oort cloud in their model did not form a smooth, featureless disk. It developed 2 spiral arms, resembling a miniature galaxy oriented vertically relative to the plane of the planets. The structure spanned roughly 0.24 light-years across, and the spiral pattern emerged naturally from the gravitational interactions that built the cloud. The team found that the gravitational pull of the planets and passing stars had surprisingly little ongoing effect on the inner cloud once it was established. The spiral arms were a fossil imprint of the formation process itself, frozen in place by the vast timescales and feeble gravitational forces at play in that remote region. This study remains a model prediction, not a direct observation. No one has imaged the spiral arms, but it represents the most detailed structural hypothesis for the inner Oort cloud to date, and it demonstrates that even a structure we cannot see can yield to careful simulation and inference. The strongest individual piece of evidence for the inner Oort cloud arrived in 2003, when astronomers Michael Brown, Chadwick Trujillo, and David Rabinowitz discovered a distant object that defied every existing category. Formerly designated Minor Planet 9377, it was given the name Sedna, after the Inuit goddess of the sea. Sedna's orbit was unlike anything previously observed. Its perihelion, the closest it ever comes to the Sun, is approximately 76 astronomical units. That places it permanently beyond Neptune's gravitational influence. Neptune orbits at 30 astronomical units, and even the most extreme scattered disk objects pass close enough to Neptune during part of their orbits to feel its pull. Sedna does not. It is gravitationally detached from every known planet. At the same time, Sedna's semi-major axis of roughly 500 astronomical units, and its aphelion near 937 astronomical units, place it far too close to the Sun to be a classical outer Oort cloud object. Bodies in the outer cloud orbit at tens of thousands of astronomical units. Sedna occupies a strange middle ground, too distant for the scattered disk, too close for the outer cloud, and completely isolated from the gravitational influence of any known body that could have placed it there. Brown and his colleagues titled their discovery paper accordingly. They called Sedna a candidate inner Oort Cloud planetoid. How did Sedna get there? Its orbit cannot be explained by any interaction with the known planets. Several hypotheses have been proposed. One suggests that a close encounter with a passing star during the Sun's early life in its birth cluster could have pulled Sedna's orbit outward and lifted its perihelion beyond Neptune's reach. Another proposes that an undiscovered massive planet, far beyond Neptune, might have shepherded Sedna and similar objects into their detached orbits. A third model invokes the combined gravitational effects of the Sun's sibling stars in its original stellar nursery, which could have perturbed nearby icy bodies into exactly the kind of orbits Sedna displays. Each scenario predicts a significant hidden population of similar objects occupying the same orbital region. Sedna is almost certainly not alone. That prediction received powerful confirmation in 2014, when astronomers discovered 2012 VP-113, another detached object with a perihelion, near 80 astronomical units, and a semi-major axis over 260 astronomical units. Like Sedna, it sits beyond Neptune's influence. Like Sedna, its orbit makes no sense within the standard planetary model. And like Sedna, it points toward a population of inner Oort cloud bodies that bridges the vast gap between the scattered disk and the outer cloud. A third candidate arrived in 2018 with the announcement of 2015 TG387, informally nicknamed the Goblin. Its discovery was not an accident. Astronomers Scott Shepard and Chad Trujillo had been conducting a systematic survey specifically designed to find objects like Sedna, using some of the most powerful wide-field telescopes on Earth, including the Subaru telescope on MAW-NU, KU in Hawaii, and facilities at Cerro Tololo in Chile. They were looking for objects moving extremely slowly against the background stars, a telltale sign of enormous distance. The search required patience on a scale that most observing programs would never tolerate. A typical Kuiper Belt object moves noticeably between exposures taken hours apart. An inner Oort cloud candidate at several hundred astronomical units might barely shift over an entire night. The Goblin revealed itself as a faint point of light inching across the sky at a glacial rate. Follow-up observations over months confirmed its orbit, and the numbers were remarkable. Its perihelion sits at about 65 astronomical units, and its semi-major axis stretches past 1100 astronomical units, giving it one of the largest known orbits of any solar system body. 2015 TG387 takes roughly 40,000 years to complete a single orbit. For most of that time, it drifts in total darkness, far beyond any telescope's reach, invisible and alone. It spends the overwhelming majority of its existence at distances where no instrument ever built could detect it. Only during a brief window of a few centuries, when it swings closest to the Sun, does it enter the range of our deepest surveys. The Goblin happened to be passing through that window during the years Shepard and Trujillo were looking. If their survey had been conducted a few thousand years earlier or later, the Goblin would have been invisible, drifting somewhere beyond 500 astronomical units with no chance of detection. This is the deeply unsettling implication. For every object like the Goblin that we catch during its brief observable window, there must be hundreds or thousands of others currently at the far ends of their orbits, invisible and uncountable. The detected objects are not the population, they are the rounding error. Dynamical models suggest that the true inner Oort cloud population could number in the millions or tens of millions, an enormous hidden census of frozen bodies on orbits so large that most of them will never be observed by human instruments. These three are almost certainly not the full list. Additional candidates with high perihelia and large semi-major axes continue to appear in deep surveys, each one adding to this emerging class of extreme trans-Neptunian bodies that seem to inhabit the innermost fringes of the Oort cloud. These objects were not born where we find them. Nothing formed at 500 astronomical units from the Sun. At those distances, the protoplanetary disk that built the planets was too thin, too cold, and too sparse to assemble anything larger than dust. Every Oort cloud object, whether it orbits at 500 astronomical units or 50,000, originally formed much closer to the Sun. Models of solar system formation suggest that most Oort cloud material coalesced in the region between roughly 5 and 40 astronomical units, the zone dominated by the giant planets. The story of how they got from there to the Oort cloud is a story of violence, chaos, and patience. During the solar system's first several 100 million years, the giant planets were not sitting quietly in their current orbits. They were migrating, shifting positions under the influence of gravitational interactions with each other, and with the massive disk of leftover debris surrounding them. Jupiter moved slightly inward. Neptune moved dramatically outward, sweeping through a dense belt of icy planetesimals. As Neptune ploughed through this material, its gravity flung enormous quantities of icy bodies onto wild, elongated orbits. Some were ejected from the solar system entirely, hurled outward at speeds exceeding the sun's escape velocity, and lost forever to interstellar space. Others were thrown onto orbits that carried them thousands or tens of thousands of astronomical units from the sun, but not quite fast enough to escape. These barely bound objects formed the raw material of the Oort Cloud, but being flung outward was not enough by itself. An icy body launched onto a highly elongated orbit would, without any additional force, eventually return to the inner solar system and pass near the giant planets again. On the next pass, it might be ejected completely or scattered onto a different orbit. The process would repeat, and over time, most objects would be lost. For the Oort Cloud to form and persist, something had to change those elongated orbits into more circular ones, lifting the perihelion, the closest point to the sun, away from the danger zone of the giant planets. Something had to detach these objects from the planets that scattered them. That something was the galaxy. Galactic tides, the differential gravitational pull of the Milky Way's mass, acted on these distant objects over millions of years. The tidal forces slowly rotated their orbital planes and shifted their perihelia outward. An object scattered by Neptune to an aphelion of 30,000 astronomical units might have its perihelion gradually lifted from 10 astronomical units to 10,000, completely removing it from the influence of any planet. Once detached, the object was trapped. It could no longer return to the inner solar system without another perturbation. It had become a permanent resident of the Oort Cloud. Passing stars in the sun's birth cluster contributed as well. During the solar system's first tens of millions of years, the sun was still embedded in a dense stellar environment. Close encounters with sibling stars provided additional perturbations, randomizing orbital orientations and further detaching objects from the planetary zone. The combination of planetary scattering, galactic tides, and stellar encounters built the Oort Cloud over a period of roughly 1 billion years. By the time the sun left its birth cluster and settled into a quieter galactic neighborhood, the cloud was largely in place. One remarkable implication of this formation model is that the Oort Cloud contains some of the most pristine material in the solar system. These icy bodies have been stored at temperatures only a few degrees above absolute zero for 4.5 billion years. They have not been significantly heated, processed, or altered since they were ejected from the inner solar system. Their surfaces may still carry the original chemical fingerprints of the protoplanetary disk from which the sun and planets formed. Water ice, carbon dioxide ice, carbon monoxide ice, methane, ammonia, and traces of more complex organic molecules are all expected to exist on Oort Cloud objects. But here is where the story takes an unexpected turn. Some models suggest that a large fraction of comets in the Oort Cloud may not have formed around our sun at all. In 2010, planetary scientist Hal Lev-Eson and colleagues published research that confronted a persistent problem in Oort Cloud studies. When they modelled the formation of the cloud using only material scattered by our own giant planets, the resulting population was too small. The models could not produce enough objects to match the estimated number of comets that the Oort Cloud must contain based on the observed rate of long-period comet arrivals. Something was missing. Either the models were wrong about how efficiently the giant planets scattered debris, or there was another source of material that the models were not accounting for. The answer they proposed was startling. The sun was born in a stellar cluster, surrounded by hundreds or thousands of sibling stars, each with its own protoplanetary disk, each forming its own planets, each scattering its own icy debris outward. In that dense stellar environment, the gravitational reach of neighbouring stars overlapped. Icy bodies ejected from one star's planetary zone could be captured by another star's gravity before escaping into interstellar space. The Sun, being a relatively massive member of its birth cluster, would have been particularly effective at capturing debris from its smaller neighbours. Levisson's simulations suggested that the Sun may have captured more comets from other stars than it retained from its own scattering process. The implication was extraordinary. Perhaps 90% of Oort Cloud objects did not form in our solar system. They formed around other stars that have long since dispersed across the galaxy and may no longer be identifiable. If this is correct, then the Oort Cloud is not simply a repository of our solar system's leftovers. It is a collection of frozen debris from multiple stellar nurseries, assembled during a brief window of close stellar proximity that ended billions of years ago. The comets we see falling through Earth's sky may carry chemical fingerprints from protoplanetary disks that formed around stars we will never identify. They are fossils not just from our own past, but from the pasts of other solar systems, other planetary formation events, other histories that played out around other suns in a birth cluster that dissolved before the Earth had cooled. This hypothesis remains debated. Not all researchers agree on the capture efficiency, or on how many comets the Sun could realistically have stolen from its neighbours. But even conservative estimates suggest that a meaningful fraction of the Oort Cloud population is alien in origin. The cloud is not purely ours, it is a mixed archive, a shared inheritance from a family of stars that grew up together and then went their separate ways. This realization changes how we think about every long-period comet that arrives in the inner solar system. When a comet falls inward and astronomers analyze its composition, they may not be sampling material from our protoplanetary disk. They may be examining a frozen fragment from a completely different stellar environment, a disk with different temperatures, different chemical abundances, different mineral content. Each comet becomes not just a time capsule from the past, but a potential message from another star's formation history, delivered to our doorstep by gravity and chance. When a long-period comet falls inward and passes close to the Sun, scientists get a rare chance to sample this ancient material. The heat sublimates surface ices, releasing gases that spectroscopes can analyze. NASA's Deep Impact mission, which struck Comet Tempel 1 in 2005, found a body covered in a deep layer of fine dust with a nucleus that was roughly 75% empty space, structurally weak and incredibly porous. Different comets show different minor compositions, suggesting that they formed at various distances from the young Sun, or perhaps around different stars entirely, before being scattered outward. Each comet is a frozen time capsule, a sample of conditions in a protoplanetary disk at a specific location and moment, preserved in deep cold storage for longer than the Earth has existed. Recent years have brought a remarkable procession of Oort Cloud comets through the inner solar system, each one adding to the evidence. In 2025 alone, multiple comets originating from the Oort Cloud were observed and tracked. C. 2025 R3, discovered by the Pan-STARRS survey, passed perihelion in April 2026 and briefly reached naked eye brightness, a vivid reminder that the Oort Cloud continues to deliver material to our doorstep. For a few weeks, observers in the right hemisphere could look up and see, with no telescope at all, a smear of light that had spent its entire existence drifting in darkness, beyond the reach of any instrument, until a gravitational nudge sent it falling sunward on a journey that began before human civilization existed. C. 2024 Eon, discovered by Polish astronomer Kuiper Belt, reached perihelion in January 2026 on a hyperbolic trajectory, meaning its outbound path will carry it out of the solar system entirely. It arrived from the Oort Cloud with an inbound orbital period measured in millions of years, and it will never return. Its visit was a one-time event. Whatever information scientists gathered during its brief passage through the inner solar system is all we will ever have from that particular frozen body. It came, it was observed, and it left forever. In March 2026, NASA's Hubble Space Telescope unexpectedly captured a comet in the process of breaking apart, a fragile Oort Cloud visitor disintegrating under the thermal stress of its approach to the Sun. The images showed the nucleus splitting into multiple fragments, shedding dust and gas as it crumbled. The event was a reminder that these ancient icy bodies, preserved for billions of years in the deep freeze of the outer solar system, are often too fragile to survive the heat of the inner solar system. Many long-period comets shatter or evaporate entirely during their first and only visit, leaving behind nothing but a trail of dust and gas. The Oort Cloud sends its emissaries inward, and the Sun destroys them. Every one of these comets is a data point. Every orbit traced backward is a thread leading to the same conclusion. There is a vast, cold, invisible structure surrounding the Sun at distances so extreme that no technology we possess can observe it directly. We know its rough size. We know its approximate population. We know its two-region structure. We know how it formed. We know what its objects are made of. And we know all of this without ever having seen it, because the evidence keeps falling out of it and landing at our feet. The Oort Cloud is the largest structure associated with our Sun, and it is entirely inferred. Every fact we have about it comes from tracing the paths of objects that left it, from modelling the physics that shaped it, and from discovering a handful of frozen bodies that may sit at its innermost edge. It is a detective case built on orbital mechanics, chemical fingerprints, and the patient accumulation of evidence over 7 decades. No photograph exists, no probe has visited, and yet the case is overwhelming. We have the evidence, we have the orbits, we have the comets falling inward like messages from a place we cannot see. But nothing prepares you for how far away that place actually is. There is a kind of distance that the human brain refuses to process, not because it is complicated, but because it is too large for the neural architecture that evolution gave us. We are built for ranges measured in footsteps, throwing distances, maybe the span of a valley or a coastline on a clear day. Our deepest instincts developed on the savannas of East Africa, calibrated for the distance between a predator and a tree. Nothing in 300,000 years of human existence prepared the mind for what the Oort Cloud demands. So let us take it slowly. Let us start with something familiar and walk outward until the numbers stop cooperating. Earth orbits the Sun at 1 astronomical unit. That is the baseline. 1 astronomical unit equals roughly 150 million kilometers. Light crosses that gap in about 8 minutes. This is a distance that already exceeds any human experience, but at least we can attach it to something real. It is the warmth on your face on a summer afternoon. It is the 8 minutes of travel time between the source of all daylight and the surface where you stand. Neptune orbits at 30 astronomical units, 30 times that Earth to Sun distance. Sunlight takes about 4 hours to reach Neptune's cloud tops. At that distance, the Sun has shrunk from the blazing disk we know to a bright point smaller than a pea held at arm's length. Neptune receives roughly 900 times less sunlight than Earth. It is a world of perpetual twilight, dim and frigid. And yet Neptune is so close, in Oort Cloud terms, that it may as well be sitting in the Sun's lap. The Kuiper Belt ends around 50 astronomical units. Voyager 1, launched in 1977, has reached approximately 170 astronomical units as of 2026. That is the farthest any human-made object has ever travelled. Voyager 1 moves at about 17 kilometers per second, more than 60,000 kilometers per hour, roughly 1.5 million kilometers per day. Every 24 hours, it adds another 1.5 million kilometers of distance between itself and everything it was built to study. At this speed, Voyager 1 is faster than any bullet, faster than any airplane, faster than any other object humanity has ever sent on an outbound trajectory except its twin. And at this speed, Voyager 1 is pathetically slow against the scale of the Oort Cloud. The inner edge of the Oort Cloud is estimated to begin at roughly 2,000 astronomical units from the Sun. Some models push it out to 5,000. Take the conservative number. At 170 astronomical units, Voyager 1 has completed less than 9% of the distance to the closest possible boundary of the cloud. It has been flying for nearly half a century. To reach 2,000 astronomical units at its current rate of 3.5 astronomical units per year, it would need approximately 520 more years. And quote, 5 centuries of unbroken flight just to touch the innermost fringe. But the inner edge is not the destination. The inner Oort Cloud extends outward to roughly 20,000 astronomical units. The outer Oort Cloud beyond that stretches to perhaps 50,000, perhaps 100,000. NASA's own estimates place the outer boundary somewhere between 10,000 and 100,000 astronomical units. At 100,000 astronomical units, the outer edge of the Oort Cloud sits approximately 1.5 light years from the Sun. 1.5 light years. That means a beam of light, the fastest thing the laws of physics permit, would take 18 months to travel from the Sun to the outermost objects that still belong to our solar system. Light that left the Sun at the start of this sentence would not arrive at the outer Oort Cloud until more than a year from now. Voyager 1, at its current velocity, would need approximately 30,000 years to reach that distance. 30,000 years ago, humans were painting animals on cave walls in southern France. Entire civilizations have been born, flourished, and been forgotten in less time than it would take our fastest spacecraft to cross the full width of the structure we are describing. Now hold one more number in your mind. Alpha Centauri, the nearest star system, sits at about 4.25 light-years from the Sun. The outer boundary of the Oort Cloud at 1.5 light-years is more than a third of the way there. Our solar system does not end in a compact neighbourhood huddled around its parent star. Its outermost gravitational possessions drift in a region of space that is closer to the next star than to most of the planets that formed alongside them. To understand what this means, walk outward through the Oort Cloud and watch what happens to the Sun. At 2,000 astronomical units, the inner edge, the Sun, is overwhelmingly the brightest object in the sky. It shines at roughly -10th magnitude, brighter than the thinnest crescent moon, a searing point of light that dominates everything around it. You would not need to search for it, it would find you. Even at this enormous distance, the Sun would be so much brighter than every other star in the sky that there could be no confusion about which one was yours. Light from the Sun would take roughly 12 days to reach you. 12 days old, every photon. But the Sun would still be unmistakable. It would still feel like home. Now move outward to 5,000 astronomical units. The Sun has dimmed to roughly -8th magnitude, still far brighter than Venus ever appears from Earth. Still the most conspicuous object in the sky by an enormous margin. The constellations around you would be identical to those visible from Earth, unchanged at these distances because the stars are so much farther away that your shift in position makes no perceptible difference. You would recognize Orion. You would see the Big Dipper. The galaxy's structure would look the same, only the Sun would be different, dimmer but still commanding. At 10,000 astronomical units, the Sun has dropped to roughly -7th magnitude. It remains brighter than Venus at its most brilliant, still obviously the dominant star in the sky, still impossible to mistake for anything else. But the gap between the Sun and the brightest natural stars has begun to narrow. Sirius, at -1.5 magnitude, is still roughly 100 times fainter, but the ratio is shrinking. The Sun is losing its authority not all at once, but by degrees. At 20,000 astronomical units, the boundary between the inner and outer Oort Cloud, the Sun has faded to roughly -5th magnitude. It is now comparable in brightness to Venus at its peak, as seen from Earth, still clearly the brightest star in the sky, still findable at a glance, but for the first time, the Sun is approaching a brightness range that the human eye associates with planets and bright stars rather than with a sun. Sunlight takes roughly 4 months to reach you. The light you see left the Sun before the current season began on Earth. You are orbiting a star that still outshines everything else overhead, but the distance between its brilliance and that of the brightest natural stars is closing with every 1,000 astronomical units you travel outward. At 50,000 astronomical units, the Sun has dropped to roughly -3rd magnitude. It is still brighter than any natural star in the sky, but only by a small margin. Sirius now shines within 2 magnitudes of it, and several other brilliant stars are not far behind. The Sun is no longer dramatically dominant. It is first among near equals. If someone unfamiliar with the constellations looked up, they would see a sky full of bright stars and would need to know which one was the Sun, because several others now approach its apparent brightness. You could still identify it by colour, a slightly yellowish point among the blue, white and orange-red neighbours. But the Sun no longer announces itself. It has joined the crowd. It is the brightest member, but only just. At 100,000 astronomical units, the outermost edge, the Sun has faded to roughly -1.7 magnitude. It is now barely brighter than Sirius. The difference between the two, less than 1/3 of a magnitude, would be almost imperceptible to the human eye. The Sun would be the brightest star in the sky, but by so thin a margin that without a chart, without coordinates, without knowing exactly where to look, you might not be able to tell which of the 2 or 3 brightest points overhead was the one you came from. One of them is your star, The others are strangers. They look essentially identical. The concept of having a home star has not vanished, but it has become a matter of information rather than perception. You know the sun is there because the math says so. Your eyes can see it, but your eyes cannot tell it apart from its neighbours. You are gravitationally bound to a star that has stopped looking special. This is the walk through the Oort Cloud. It begins at a distance where the sun is overwhelmingly unmistakably yours, and ends at a distance where it is merely one bright star among several, indistinguishable from its neighbours without a chart. The transition is not sudden. It is a slow, relentless loss of dominance that takes place over tens of thousands of astronomical units. A fade so gradual that at no single point can you say, the sun stopped mattering. It just becomes less and less special, step by step, until it blends in. And at every point along that walk, the gravity holding you to the sun has weakened in lockstep with the light. At 50,000 astronomical units, solar gravity is roughly 2.5 billion times weaker than it is at Earth's distance. The sun's gravitational pull still exists out there, still technically dominant over the gravity of other stars, but only barely, and not for much longer as you move outward. The sun does not command these objects, it whispers to them, and the whisper gets softer with every additional 1,000 astronomical units of distance. Consider what an orbit looks like at that range. An icy body circling the sun at 50,000 astronomical units takes approximately 11 million years to complete a single orbit. 11 million years. The last time that body was in the same part of its orbit, there were no humans on Earth. There were no great apes. The Mediterranean Sea had dried up and refilled. Entire species of mammals had evolved, spread across continents, and gone extinct. When that object reaches this point in its orbit again, 11 million years from now, there is no guarantee that complex life will still exist on Earth. The orbit of a single Oort Cloud body spans more time than most lineages of large animals have ever survived, and there may be 1 trillion of them. Estimates for the population of the outer Oort Cloud alone range from hundreds of billions to roughly 1 trillion objects larger than 1 kilometre across. The inner cloud may contain several times more. The total mass of all these bodies combined is modest by planetary standards, perhaps a few Earth masses, but the sheer number of individual objects spread across such an enormous volume of space creates a density so low that the word empty barely begins to capture it. Imagine the outer Oort Cloud as a hollow sphere with an inner radius of 20,000 astronomical units and an outer radius of 100,000 astronomical units. The volume of that shell is staggering. If you placed 1 trillion objects inside it, each one would be separated from its nearest neighbour by an average distance of roughly several billion kilometres. For comparison, the distance from Earth to Neptune is about 4.5 billion kilometres. Oort Cloud objects are spaced apart by gaps comparable to the full width of the planetary solar system. Each frozen body drifts in its own private void, surrounded by nothing, orbiting a star it can barely see, with its nearest companion just as isolated and just as alone. Think about what that isolation means. Really sit with it for a moment. A body in the outer Oort Cloud has no neighbour it could interact with gravitationally. It has no sunlight worth mentioning. Its surface temperature hovers just a few degrees above absolute zero, warmed only by the faint background radiation of the universe itself. The leftover glow of the Big Bang stretched to microwave wavelengths. At roughly 2.7 Kelvin, the surface of an outer Oort Cloud object is colder than anything in the inner solar system, colder than the night side of Pluto, colder than the shadowed floors of permanently dark lunar craters. It is as cold as empty space itself, because at that distance, the sun contributes almost nothing. No weather, no geology, no erosion, no seasons, no tides, nothing happens to it. It simply exists, following a slow, enormous orbit through darkness, unchanged since the solar system was young. Its surface, if you could examine it, would look the same as it did 4 billion years ago. The same ices, the same dust grains, the same organic molecules, frozen in place since the protoplanetary disk dissipated and the sun ignited. No process has touched it. No force has altered it. It is a perfect fossil, suspended in a silence so complete that the concept of sound has no meaning. If it were conscious, it would experience nothing, No stimulus, no change, no event for millions of years at a stretch. The stars overhead would shift by imperceptible fractions as the galaxy rotated. The sun would drift slowly among the background constellations, indistinguishable from any other yellow dwarf. Occasionally, over millions of years, a distant star might brighten slightly as it approached and then dim again as it receded, its closest pass still measured in light years. These would be the only events in a timescale so vast that entire geological periods on Earth would pass between one discernible change and the next. And then, perhaps, a faint gravitational twitch from a passing star, a light year away, shifts its orbit by a fraction of a degree. The change is too small to notice. Nothing looks different. Nothing feels different. But the math has changed. The object's perihelion has dropped by a few hundred astronomical units. That shift will take millions of years to manifest as anything observable. But eventually, the object's orbit carries it closer to the Sun than it has been in billions of years. The temperature rises, barely, a fraction of a degree. Then another. Ices that have not sublimated since before the Earth had continents begin to stir. Gas escapes from the surface. A faint haze forms. The object, for the first time in its existence, begins to change. It is becoming a comet, and millions of years later, it arrives in the inner solar system, blazing with a tail, and someone on Earth points at the sky and says, "Look, that is the life cycle of an Oort Cloud body. Billions of years of absolute nothing. Then one nudge, then millions of years of falling, then a few weeks of glory, then destruction, or a long, slow return to the dark." This is not a cloud in any visual sense. It is a cloud only in the statistical sense, a region of space where the probability of encountering an icy body is slightly higher than in the truly empty interstellar void beyond. If you could somehow teleport into the Oort Cloud and look around, you would see nothing. No ice, no comets, no debris, just stars in every direction, indistinguishable from any random point in interstellar space. You would not know you were inside a structure at all. You would have no way to determine, without instruments, which of the thousands of stars overhead was your own sun. The cloud is invisible not because it is hidden, but because it is almost entirely made of nothing. A single drop of water suspended in the center of an Olympic swimming pool occupies a larger fraction of that pool's volume than any individual object occupies within the Oort Cloud. To put the emptiness another way, imagine taking every object in the outer Oort Cloud, all trillion of them, and compressing them into a single mass. The result would be a body with a mass of perhaps a few Earths, a respectable but not extraordinary amount of material. Now, spread that mass across a spherical shell whose inner surface begins at 20,000 astronomical units and whose outer surface extends to 100,000. The volume of that shell is roughly 1.5 times 10 to the 40th cubic kilometers. The average density of matter within it is roughly 1 billion times lower than the best vacuum ever created in a laboratory on Earth. The Oort Cloud is emptier than any environment humans have ever created or experienced, a void that no vacuum chamber on Earth has come close to replicating. It is a monument to nothingness, punctuated by specks. This vast emptiness makes the Oort Cloud extraordinarily difficult to study by any means other than inference. Objects within it do not reflect enough sunlight to be photographed. They do not emit detectable heat. They do not produce radio signals or gravitational waves. The only way we know they are there is when one of them leaves. When a gravitational perturbation dislodges an icy body and sends it falling inward, it spends hundreds of thousands or millions of years spiraling through empty space before it reaches the inner solar system and becomes visible as a comet. By the time we see it, it has already been travelling longer than some geological eras. In 2025, the solar system received a visitor that illustrated the Oort Cloud's relationship to the galaxy from the opposite direction. On July 1st of that year, the Atlas Survey Telescope in Chile detected a new object on an unusual trajectory, designated 3I, Atlas. It was quickly confirmed as the third known interstellar object ever observed, following Oumuamua in 2017 and Borisov in 2019. 3I Atlas was not a member of our Oort Cloud. It was a comet from another star system, a frozen body that had been expelled from some distant planetary system elsewhere in the Milky Way. and had been drifting through interstellar space at roughly 58 kilometers per second before the sun's gravity bent its path into a hyperbolic flyby. It reached perihelion in late October 2025, passing just inside the orbit of Mars at roughly 1.36 astronomical units from the Sun, and was studied intensely by Hubble, the James Webb Space Telescope, and ground-based observatories around the world before it swung back outward and left the solar system forever. 3I Atlas was dramatically larger and brighter than the first two interstellar visitors. Oumuamua had been tiny and inactive, a strange, elongated body just a few hundred meters across that showed no cometary tail. Borisov was a more traditional comet, but still small. 3I Atlas, by contrast, had a nucleus estimated at roughly 1.3 kilometers across, surrounded by an enormous coma of carbon dioxide gas and dust that extended hundreds of thousands of kilometers. It reached approximately 9th magnitude near perihelion, putting it within range of amateur telescopes. For the first time, an interstellar comet was bright enough to be studied in real chemical detail, and the chemistry was extraordinary. James Webb Space Telescope observations revealed spectral signatures consistent with ancient, cold-stored ices from a protoplanetary disk, very different from our own. The comet carried chemical fingerprints from another stellar environment, a direct sample of planet-forming material from around a distant, unknown star. Researchers describe the spectral data as one of the most significant cometary measurements ever obtained. 3I Atlas was not just a passing curiosity. It was a laboratory delivery from another solar system's equivalent of the Oort Cloud. What makes 3I Atlas relevant to the Oort Cloud story is what its detection implies about the space between stars. Calculations based on its discovery suggest that at any given moment, trillions of similar interstellar objects may be drifting through the volume of space enclosed by the Sun's gravitational influence. The estimate is staggering. For every 3I Atlas-sized body that happens to pass within the orbit of Jupiter, where our surveys can detect it, trillions more are cruising through the vastness of the outer solar system undetected. Some of these objects are passing through, others may be temporarily captured or deflected. The space that the Oort Cloud occupies is not exclusively solar territory. It is a region where the Sun's gravity dominates, but where interstellar travelers are constantly passing through, mixing with the Sun's own icy population in ways that make any clean boundary meaningless. The total mass of interstellar objects currently drifting through the Sun's gravitational domain may approach several Earth masses, comparable to the estimated mass of the Oort Cloud itself. This means the space between the Kuiper Belt and the outer Oort Cloud is not empty. It is populated by a mix of solar and alien debris, bound and unbound, permanent and transient, all drifting through the same enormous volume of near-absolute darkness. The distinction between what belongs to our Sun and what is merely passing through becomes increasingly blurred at these distances. 3I Atlas also reinforced a broader implication. If our Sun has an Oort Cloud, other stars likely do as well. The galaxy may be filled with overlapping shells of icy debris, each star surrounded by its own invisible halo of frozen remnants, blending into each other across interstellar distances. The Oort Cloud is not a unique solar feature. It is probably a universal one, repeated around hundreds of billions of stars across the Milky Way. This brings the Oort Cloud scale into its most disorienting context. The structure is not merely large by solar system standards, it is large enough to overlap with the equivalent structures of neighbouring stars. The Sun's outermost icy bodies orbit at distances where the next star's outermost icy bodies may be drifting on roughly similar trajectories. The boundary between one star's gravitational domain and another's is not a wall or a fence. It is a gradual transition zone, a region where objects may not clearly belong to any single star, where gravitational loyalties shift over millions of years as the Sun and its neighbours move through the galaxy. Voyager 1 will enter this transition zone eventually. Not soon, not within any living person's lifetime, but the spacecraft is headed outward, and it will not stop. By the early 2030s, its power supply will likely fail and its transmitter will go silent. It will coast onward, unpowered and uncontactable, carrying a golden record etched with sounds and images of Earth, a message in a bottle thrown into an ocean too large to cross. In roughly 500 years, it will reach the inner edge of the Oort Cloud. In 30,000 years, it will exit the far side, and in about 40,000 years, it will pass within roughly 1.7 light-years of a small red dwarf star called Ross 248. At that point, Voyager 1 may technically be closer to another star than to the Sun, but it will still be within the Sun's gravitational sphere of influence, still arguably a solar system object, still bound however weakly to the star that built it. The phrase solar system does not mean what most people think it means. It does not refer to the Sun and its 8 planets. It refers to the Sun and everything gravitationally bound to it. And the Sun's gravitational reach extends over a volume of space so enormous that it takes light more than a year to cross it. Within that volume, 1 trillion icy bodies orbit in silence. Interstellar wanderers pass through constantly. The Sun's authority weakens with every additional astronomical unit of distance, but it does not vanish. It fades. It thins. It becomes a suggestion rather than a command. And the objects at the outer edge obey that suggestion only because nothing stronger has yet pulled them away. One of the hardest things to internalize about the Oort Cloud is that it is not a distant wall at the edge of the solar system. It is the solar system. The planets are the anomaly. The inner solar system, with its rocky worlds and gas giants and asteroid belt and moons, occupies a tiny fraction of the Sun's gravitational domain. Most of the solar system, by volume, is Oort Cloud. Most of the solar system is dark, empty, cold, featureless, and unimaginably far from anything we have ever experienced. The planetary zone is the exception. The Oort Cloud is the rule. Every map that draws the solar system as a neat disk of planetary orbits ending at Neptune or Pluto is committing an act of omission so extreme that it distorts our entire understanding of where we live. It is like drawing a map of the Earth that shows only your house and labels the rest of the planet as blank space. The Oort Cloud does not appear on most diagrams because it cannot appear at any printable scale. If the planetary orbits were drawn at a size visible to the naked eye, the Oort Cloud would extend beyond the edges of the room, beyond the building, beyond the block. Even logarithmic scale diagrams, the kind NASA uses to compress the solar system's distances into a single image, struggle to convey the true proportions. They compress the Oort Cloud into a thin band at the edge of the frame, giving the visual impression that it is a minor addition to the planetary system. It is not. It is the dominant feature. The planets are decorations near the center of a gravitational territory so vast that most of it has never been visited, never been observed, and never will be. The numbers stop cooperating at this range. 30 astronomical units to Neptune, 2,000 to the inner Oort Cloud, 100,000 to the outer edge, 170 for Voyager 1's current position, 500 years to reach the front gate, 30,000 to reach the back, 1 trillion objects, a few Earth masses, 1.5 light-years across. These figures sit on the page and refuse to assemble into anything the imagination can hold. They are too large, too sparse, too slow, too far. They describe a structure that exists at the intersection of the real and the incomprehensible, too well evidenced to deny and too vast to picture. But the most unsettling thing is not how far the Oort Cloud extends. It is what happens at its outer edge, where the Sun's authority dissolves and the galaxy takes over. Borders exist because people need them. We draw lines on maps, build fences between properties, mark the edges of countries with rivers and mountain ridges and concrete walls. These boundaries satisfy something deep in the way we organize reality. Here ends one thing. There begins another, inside and outside, ours and theirs, the known and the unknown. Borders give the world structure. They make territory comprehensible. They let us say where something is by defining where it is not. The solar system has no border. This is not a poetic statement. It is not an abstraction designed to sound profound. It is the physical truth, confirmed by orbital mechanics, gravitational physics, and 7 decades of accumulated observation. The Sun's influence does not terminate at a line. It does not hit a wall. There is no distance at which solar gravity drops to 0 and the Sun stops mattering. Gravity has infinite range. It weakens with distance, falling off with the square of the separation, but it never reaches 0. At 100 astronomical units, the Sun's pull is 10,000 times weaker than at Earth's orbit. At 10,000 astronomical units, it is 100 million times weaker. At 100,000 astronomical units, it is 10 billion times weaker. The numbers plummet, but they never arrive at nothing. There is always a residual pull, a faint gravitational whisper from a star that is by now indistinguishable from the background sky. What changes is not whether the sun pulls, but whether anything else pulls harder. And that is where the Oort Cloud meets the galaxy. The Milky Way is not a passive backdrop. It is a massive gravitational system in its own right, containing hundreds of billions of stars, vast clouds of gas and dust, and an enormous halo of dark matter. Every object in the solar system, including the Sun itself, orbits the galactic center. The Sun completes one galactic orbit approximately every 230 million years, carrying the entire solar system with it. But the galaxy does not pull on the solar system as a single uniform force. It pulls differently on different parts, depending on their position relative to the galactic plane and the galactic center. This differential pull is called the galactic tide. The galactic tide works subtly. It does not rip objects away from the Sun in dramatic bursts. It applies a slow, steady torque to the orbits of distant bodies, gradually rotating their orbital planes and shifting their closest and farthest points from the Sun over millions of years. For objects in the inner solar system, the effect is negligible. The Sun's gravity is so dominant near the planets that the galactic tide is irrelevant, but at the distances where the Oort Cloud resides, the balance shifts. At tens of thousands of astronomical units, the Sun's gravity has weakened to the point where the galactic tide becomes a significant competing force. The tide can rotate the orbit of an Oort Cloud body so that its perihelion drops from tens of thousands of astronomical units down to just a few dozen. When that happens, the object falls inward. It crosses the orbits of the giant planets. It enters the inner solar system. Its ices begin to sublimate. It becomes a comet. This is the dominant mechanism by which long-period comets are delivered to the inner solar system. Not collisions, not explosions, not sudden gravitational catastrophes. The galaxy itself, pulling gently on the Sun's most distant possessions, slowly redirecting orbits over timescales longer than most species survive. The galactic tide is patient. It has been operating for 4.5 billion years. It will continue operating for billions more, and with every million years that pass, it peels another thin layer of icy bodies from the Oort Cloud and feeds them inward. Researchers confirm that the galactic tide is more important than individual stellar encounters in shaping the overall flux of long-period comets. When astronomers model the delivery rate of new comets from the Oort Cloud, the tide accounts for the majority of the signal. Passing stars contribute as well, but on a statistical basis, it is the slow, relentless gravitational gradient of the Milky Way that does most of the work. But passing stars are not irrelevant. They provide the other major source of perturbation, and their effects can be dramatic. Stars move. The Sun orbits the galactic center, and so does every other star in the neighborhood. This means that over millions of years, other stars occasionally pass relatively close to the solar system. Most of these encounters are distant and insignificant. A star passing at several light years has no measurable effect on anything in the Oort Cloud, but once in a while, a star passes close enough to matter. Once in a very long while, a star passes close enough to carve a path directly through the cloud itself. Data from the Gaia spacecraft, which has measured the positions, motions, and distances of more than 1 billion stars with extraordinary precision, has allowed astronomers to identify past and future stellar encounters with the solar system. Gaia revealed that dozens of stars have passed or will pass within a few parsecs of the Sun over the past and coming millions of years. Most of these encounters are too distant to significantly affect the Oort Cloud, but a handful stand out as genuinely consequential. The most significant upcoming encounter involves the star Gliese 710, a low-mass star currently about 19 parsecs away. Gaia measurements confirmed that Gliese 710 is heading toward the solar system and will pass through the outer Oort Cloud in approximately 1.3 million years, coming within roughly 10,500 astronomical units of the Sun. The star has roughly 6/10 the mass of the Sun and is traveling at about 14.5 kilometers per second relative to our system. 10,500 astronomical units is deep inside the Oort Cloud. This is not a grazing flyby at the outermost edge. Gliese 710 will penetrate well into the cloud's populated regions, passing close enough to gravitationally perturb enormous numbers of icy bodies. Simulations of this encounter suggest that the star will alter the orbits of comets along its trajectory, particularly those in the inner portions of the cloud near its path. Some of these perturbed objects will be sent inward toward the Sun. Others will be ejected outward into interstellar space. The result will be a comet shower, not immediate, but building over a period of several million years as disturbed objects slowly migrate onto new orbits and begin their long fall inward. The passage itself will take roughly 64,000 years as the star crosses the cloud's full extent, and the gravitational effects will ripple outward for millions of years after the star has departed. This is not the first time the solar system has experienced such an encounter, and it will not be the last. Roughly 70,000 years ago, a small binary star system now called Schultz's star passed within approximately 52,000 astronomical units of the Sun. That placed it within the outer Oort Cloud itself. Think about what that moment was like. 70,000 years ago, Homo sapiens shared Europe with Neanderthals. Language may have existed, but writing did not. No one on Earth understood what a star was. No one knew the Sun was a star. They knew the sky. They watched it every clear night, the only illumination after sunset apart from their own small fires. The band of the Milky Way stretched overhead like a river of light, and they told stories about it, stories we will never recover. Individual stars were markers of season and direction. The bright ones had significance. The patterns they formed carried meaning, though not the meaning we assign today. The sky was not a map of physics. It was a ceiling of stories, a canopy of spirits or gods or ancestors depending on the culture and the era, a reliable presence that returned every evening when the sun disappeared and the world went dark. They watched it with the same eyes we have, the same retinas, the same sensitivity to colour and brightness, the same ability to resolve points of light separated by fractions of a degree. They saw the same stars we see, but they had no framework for understanding that one of those points of light was the furnace keeping them alive, or that the warmth on their skin during the day and the stars overhead at night were manifestations of the same physical process, or that the seemingly permanent arrangement of lights above them was actually a snapshot of objects in motion, each one travelling its own path through a galaxy they could not have conceived of. And on one particular stretch of nights, spanning a period too brief to register against the timescale of the sky's slow turning, something was up there that no human eye could detect. A dim red dwarf and its even dimmer brown dwarf companion were drifting through the outermost reaches of the Sun's territory. 70,000 years before anyone would know what the Sun's territory meant. The idea of a solar system would not be conceived for another 69,000 years, and overhead, invisible against the background sky, Schultz's star was passing through. Schultz's star was faint. At its closest approach, it would have been far too dim to see with the naked eye, perhaps only visible through a modern telescope if one had existed. No one on Earth noticed. No one could have. The star passed through the outer Oort Cloud, exerting its modest gravitational influence on the icy bodies in its vicinity, and then continued on its way. The encounter lasted a cosmically brief period. The star came, it tugged, it left. It is now roughly 20 light-years away, an unremarkable red dwarf in the constellation Monoceros that would have attracted no attention whatsoever if Gaia data had not traced its path backward and revealed where it had been. But its passage was not without consequence. Any icy body that happened to orbit near Schultz's star's trajectory received a gravitational perturbation. Most of these perturbations were tiny, shifts of fractions of a degree in orbital orientation, minor adjustments to perihelia. But in the Oort Cloud, tiny perturbations compound over millions of years. An object whose perihelion was nudged downward by a few hundred astronomical units might spend the next 2 million years slowly spiralling inward, its orbit gradually evolving under the influence of galactic tides until it crosses the threshold where the giant planets can grab it and redirect it toward the inner solar system. Those comets are still falling. Right now, in 2026, icy bodies perturbed by Schultz's star's passage 70,000 years ago are drifting inward through the vast space between the Oort Cloud and the planetary zone. They will not arrive for thousands or millions of years. When they do, they will appear in Earth's sky as new long-period comets, and no one will know that their journeys began because a dim red dwarf drifted through the sun's backyard before the invention of agriculture. The comet will carry no record of the encounter. It will simply arrive, ancient and anonymous, a consequence of a cause that occurred before our species had language to describe it. Over the full 4.5 billion year history of the solar system, thousands of stars have passed close enough to disturb the cloud's outer regions. Each encounter reshuffled some orbits, ejected some objects, and sent others falling inward. The Oort Cloud has been continuously stirred, shaped, and eroded by these passages since the day it formed. It is not a fossil, it is a living system, constantly responding to forces that originate far beyond the sun's control. The combined effect of galactic tides and stellar encounters gives the Oort Cloud its dynamic character. This is not a static structure, frozen in place since the solar system formed. Objects are being lost from the outer edge continuously. Some fall inward and become comets. Others are stripped away by passing stars or by the galactic tide and drift off into interstellar space, no longer bound to the sun. The Oort Cloud is slowly shrinking, losing mass to both the inner solar system and the galaxy over billions of years. At the same time, the inner Oort Cloud may be replenishing the outer cloud. Objects in the denser inner region, too tightly bound to be easily dislodged by the galactic tide, can be gradually migrated outward over extremely long timescales. The inner cloud acts as a reservoir, feeding the outer cloud even as the outer cloud loses material. This dynamic equilibrium is one of the reasons the Oort Cloud still exists after 4.5 billion years. Without the inner reservoir, the outer cloud might have been entirely depleted long ago. The region where the sun's gravitational dominance gives way to the galaxies is described by a concept called the Hill sphere. In orbital mechanics, the Hill sphere defines the volume around a body within which that body's gravity dominates over the gravity of a larger body it orbits. For the sun orbiting the center of the Milky Way, the Hill sphere extends to roughly 100,000 to 200,000 astronomical units, depending on the sun's current position in its galactic orbit and the local density of the galactic environment. Beyond the Hill sphere, the galaxy wins. Objects at those distances are no longer gravitationally bound to the sun. They belong to the Milky Way's general gravitational field, free to drift among the stars. The outer boundary of the Oort Cloud is thought to roughly coincide with the sun's Hill sphere. This is not a coincidence. Objects that were once scattered outward from the planetary zone could only be retained by the sun if they remained within the Hill sphere. Anything flung beyond that limit was lost to interstellar space. But the Hill sphere is not a sharp boundary. It is not a fence. It is a gradient. At 90,000 astronomical units, the sun's gravity still dominates, but only slightly. At 110,000 astronomical units, it might not. At 150,000, it almost certainly does not. The transition is gradual, and it depends on local conditions. When the sun passes through a denser region of the galaxy, the Hill sphere contracts. When it moves through a less dense region, the sphere expands. The outer boundary of the solar system literally breathes, expanding and contracting in response to the galactic environment, shifting by thousands of astronomical units over the course of a single galactic orbit. This means there is no fixed edge. The solar system's outer boundary is a moving target, defined not by a permanent feature, but by a temporary gravitational balance between the sun and the galaxy. Objects that are bound to the sun today might not be bound to it 100 million years from now if the sun passes through a denser galactic region and its Hill sphere contracts. The Oort Cloud is not just being eroded by external forces, its very boundary is shifting, redrawing the frontier of the solar system on timescales that are long by human standards but brief by cosmic ones. And the erosion will not stop. It will accelerate. In roughly 5 billion years, the sun will exhaust the hydrogen fuel in its core. It will swell into a red giant, expanding to perhaps the orbit of Earth, engulfing Mercury and Venus, and flooding the inner solar system with enough heat to melt the surfaces of the remaining rocky worlds. But the more significant effect for the Oort Cloud will not be the heat, it will be the mass loss. As the sun expands, it will shed enormous quantities of material through powerful stellar winds, losing roughly half its current mass over the course of several 100 million years. This material will disperse into interstellar space, thinning the Sun from a 1 solar mass star to approximately half a solar mass. That mass loss changes everything at the outer edge. Gravity depends on mass. Halve the Sun's mass, and you halve the gravitational pull at every distance. Objects that are barely bound today, orbiting at the outer fringe of the Hill sphere with orbital periods measured in millions of years, will find themselves no longer held. The Hill sphere will contract dramatically as the Sun loses its grip. The outer boundary of the Oort Cloud will shrink inward. Trillions of icy bodies that have orbited the Sun for 4.5 billion years will gradually slip away, their orbits widening past the point of no return, drifting outward into interstellar space with no force to bring them back. The Oort Cloud will dissolve, not all at once, not in a dramatic burst. Slowly, over hundreds of millions of years, the Sun's shrinking gravitational authority will release its most distant possessions. The outermost objects will go first, followed by progressively closer ones as the Hill sphere continues to contract. The inner Oort Cloud, more tightly bound, will survive longer, but even it will eventually lose its outermost members. By the time the Sun finishes its red giant phase and collapses into a white dwarf, a dense stellar remnant roughly the size of Earth but with perhaps half the Sun's original mass, the Oort Cloud will be a fraction of its current self. Most of its population will be gone, released into the galaxy, orphaned debris from a star that no longer has the authority to hold them. These released objects will drift among the stars. They will join the population of interstellar wanderers, the same population that sent 3I Atlas through our solar system in 2025. They will become someone else's interstellar visitors, icy fossils from a dead star's youth, carrying chemical fingerprints of a protoplanetary disk that formed 10 billion years before their arrival. If another civilization in another stellar system detects one of these objects falling through their sky, they will see a comet from a sun that died long ago. The solar system does not just fade at its edges in space, it will eventually fade in time. The dissolution is not only spatial but temporal. The Oort Cloud is the Sun's most fragile possession, the first thing it will lose as it ages, the first boundary to retreat, the first territory to surrender to the galaxy. The philosophical weight of this fact is difficult to overstate, and this is where the story of the Oort Cloud becomes something more than a lesson in distances. We are accustomed to thinking of the solar system as a place, a location with a defined shape, a known population, and a clear extent. The textbook diagram reinforces this intuition. 8 planets, a few belts of debris, a boundary somewhere past Neptune or Pluto. Inside the boundary is the solar system. Outside is everything else. The border is clean. The territory is settled. The map is finished. The Oort Cloud destroys this picture entirely. There is no clean border. The solar system does not end. It dissolves. The Sun's gravitational influence weakens gradually, contested at every step by the galaxy's competing pull. The outermost icy bodies orbiting the Sun are so loosely held that a nudge from a passing star or a century of galactic tidal torque can release them. Objects drift out of the Sun's control and into interstellar space. Other objects, remnants of other stars' Oort clouds or interstellar debris, drift in. The boundary between what belongs to the Sun and what belongs to the galaxy is not a line. It is a fog, a gradient of ink spreading on wet paper, thinning outward until the edge is nowhere and everywhere at the same time. This is unsettling because it undermines the human need for definite territory. We want to know where we live. We want to point at a map and say, here is the solar system, and there is everything else. The Oort Cloud denies that satisfaction. It tells us that our solar system is not an island. It is a hill, a gentle rise in the gravitational landscape of the galaxy, surrounded on all sides by other hills, each one another star with its own retinue of frozen debris. The valleys between the hills are not empty. They are filled with interstellar wanderers and shared gravitational territory. No star's domain ends cleanly. They all fade into each other, blending at the margins into a galactic commons where ownership is determined by the slow, silent arithmetic of gravity and distance. The Sun has no fence. It has a field. The field weakens with distance. At some point, the field is so weak that calling it the Sun's influence becomes a matter of definition rather than physics. An icy body at 100,000 astronomical units technically orbits the Sun, but its orbital period is longer than the history of complex life on Earth, and it moves so slowly relative to the Sun that its motion is almost indistinguishable from the general drift of interstellar material. It responds to the galaxy almost as strongly as it responds to the Sun. It belongs to the solar system only in the most provisional and temporary sense, a resident whose lease could be revoked at any time by a passing star or a shift in the galactic tide. And yet these marginal, half-bound, barely solar objects are part of the solar system. They orbit the Sun. They carry the chemical fingerprints of the protoplanetary disk that formed the planets. They are made of the same ice and rock that built the cores of Uranus and Neptune. They are siblings of the planets, scattered outward instead of inward, stored in the deep cold of near interstellar space for longer than the Earth has had an atmosphere. They are the solar system's most distant and most neglected members, and they outnumber the planets by a factor that renders planetary astronomy a study of rare exceptions. The terrifying truth about the Oort Cloud is not just that it is far away. It is not just that it is invisible, or that it contains 1 trillion objects, or that Voyager 1 will need 30,000 years to cross it. The terrifying truth is what it reveals about the nature of the solar system itself. The solar system is not the 8-planet diagram on the classroom wall. It is a gravitational gradient, vast and diffuse, stretching more than a light year in every direction, populated mostly by emptiness and cold, held together by a force so weak at its edges that the galaxy can steal from it at will. The familiar planets are a tiny bright core at the center of this gradient, and the Oort Cloud is everything else. The planets are where the Sun's story is loudest. The Oort Cloud is where it becomes a murmur, and somewhere past the outer cloud, the murmur fades to nothing, and the Sun is just another star, and the solar system stops meaning anything at all. Not because it hits a wall, not because something blocks the way, but because the gradient thins to the point where the distinction between inside and outside ceases to have physical meaning. The solar system does not end, it fades. The Sun's gravitational voice does not stop speaking. It just becomes so quiet that the galaxy's voice drowns it out. And at that point, you are no longer in the solar system because you are no longer anywhere specific. You are in the space between stars, the shared gravitational commons where no single sun dominates, where frozen debris from a dozen stellar systems drifts together without allegiance, where the concept of belonging to a particular star loses all definition. This is the real edge of the solar system, not a place, a process, a slow dissolution from territory into ambiguity, a fading that takes place over thousands of astronomical units, over millions of years, over distances so large that the human brain abandoned comprehension long before the Sun's gravity abandoned its grip. Jan Oort proposed the cloud in 1950. He never saw it. Nobody has. Nobody will. At least not in the way we see planets and moons and rings. The Oort Cloud will remain an inferred structure, known through its effects, deduced from orbits and simulations, and the endless slow arrival of comets that began their journeys before our species existed. It is the largest thing associated with our Sun, and it is a ghost. A presence felt through mathematics and the faint gravitational footprints of objects that departed it millions of years ago. But it is real. The comets confirm it, the orbits demand it, the models reproduce it, and its existence means that the solar system you grew up imagining, the tidy planetary diagram with a clear edge and a manageable size, was never more than a convenient fiction. The real solar system is darker, colder, emptier, and more enormous than any illustration can convey. It stretches outward for more than a light year. It contains more objects than you can count in a lifetime. It fades at its edges into the galaxy that made it, and it has no border, no wall, no line in the dark where you can stand and say, "Here the Sun's kingdom ends." It just fades, and the fading is the most honest thing about it, because the universe does not draw borders, it draws gradients, and we live inside one, warmed by a star whose reach extends far beyond its light, surrounded by 1 trillion frozen witnesses to a formation event that happened before the Earth had oceans, drifting through a galaxy that treats our Sun as just another point of gravity in an ocean of points, unremarkable, unexceptional, and without a clear edge to call its own. The solar system never really ends, it just stops mattering, and the Oort Cloud is where that long, quiet, terrifying process begins.